D5 in our review of basic physics. Work and kinetic energy. Now let's do work first. Say A, work. And let's say we're pushing appliances in a warehouse across the room. So there's a force involved, applying the force, and a distance that has to be traveled. So let's say here we're going to go from there some distance to the right. Now if we're paying people to push these things in a warehouse and there's some truck, say some truck out here that we're going to load things up with, you're going to want to pay people more if they're pushing a longer distance, and you're going to pay them more if they're pushing with a appliance that needs a stronger force, and we're assuming it's a constant force that we'll be applying across the floor. Now we're going to pay them not by the hour, but by the actual work that they do. And we're going to consider the force and the distance. So since the work is going to be proportional to the force, if they're pushing, say, refrigerators versus, say, a dishwasher or something that's not requiring such a force, that's important. And also the work is proportional to the distance that they need to move. Since in the warehouse, some of the appliances are way to the left and some are near the middle. So what we're going to take for our definition of work is the force times the distance. That's what we're going to do. Now let's look at the units. And when I use my brackets here for units, I use a little different convention than what they usually do with dimensions. And this is called dimensional analysis. For example, if they say, what is the dimensions of X, they'll say that's a length, and they'll put capital L. So you'll have capital L for length, capital T for time, and capital M for mass, the big three. But I don't like doing that. My convention is, it's easier for me to just say this would be meters, and say time would be seconds. So that's how I like to think. So therefore here, this new quantity that we're looking at, physical quantity, has a number and a unit, is going to be the product of the dimensions for force and distance. Now force we have is newtons, and for distance, meters. So I prefer this notation. Now, if we look at this, there's a definition. This is exactly by definition. This is considered to be J for joule. Now remember, when we write out Newton and Joule, these names of scientists, we will use a lowercase. So if I wrote that out like 1 joule, I would write it like that. 2 joules, I would put an S on the end, like that. James Joule, a very, very important physicist, scientist in the history of physics. Now we know that the Newton, if we do some more analysis here, the dimensions for the Newton, well, that's Newton's force. Oh, here actually I should be putting an F here. So I'm going to be consistent. I want to use the bracket. I want to use the actual letter for the particular physical quantity. So that's a force, which is newtons. And here, since this is equal to F equals ma, now you have to be careful. This m is a mass because it's in a formula. And when we extract the units, this m is meters. So here, you would have the units for m and the units for a. And the m would be kilograms. And the acceleration would be meters per second squared, like that. So this is a little bit of a review of a physical quantity we have already seen. And I wanted to do this to emphasize that when we put the meters in to multiply the force, then the joule is going to be a kilogram meters squared over second squared. I'm emphasizing that you have the big three here. You see, this is the meters, the length, the time, and the mass. So if you wanted to do this in the traditional way, they would say m for mass, they would say L for length, and they would say T for time. And in this course, or physics review, Physics 1, pretty much I can derive every physical quantity in the whole course in terms of the big three, the mass, the length, and the time. So it's always good when we introduce a new formula and have a new physical quantity that we understand the units. And this would be in the MKS system to use the M for meters, K for kilogram, and S for seconds. Notice that here we have two cases of zero. In other words, people not doing their job. One is a person that would like to just have no force, and this is the zombie. Person just walking around pushing air, not pushing anything. So you don't pay that person anything. That are walking across the warehouse, they have a D, but no force, no money, no work. And then another way to get would be D is equal to zero. In other words, here I would say you're up against the wall. Up against the wall. So if you're going to just say push against the wall and you have a lot of force, say F is not zero, but since you're not moving, you're not pushing, you're not moving the wall, you're not doing your job. You get nothing, you get zero. And you can also have a case where work is zero by having both F equals zero and D equals zero, and we'll call that laying down on the job. And then you can figure out how many dollars or euros or whatever you want to pay per the unit's going to be your Newton meters, say Newton meters. Now, we're not taking into consideration here that if you actually have a force pushing up a little bit, that it might be easier to push things across the floor. This is a very simple model where you're pushing the forces this way and the distance is along the direction of the force. Now, in more general though, you can imagine pulling with a force where there is an angle theta here with respect to the direction that you're moving. Say you're going in this direction here. Say you're going to go, say distance d. And you can think of these as vectors that we're going to go along this d here. And we're applying a force here, which is a vector. And this is a vector. And there's an angle between them. Then the definition of the work for this case is to take the force magnitude here and take the cosine of theta to line up with the component that let's say you have in the direction of the displacement. So F cosine theta times D, or you might just say FD cosine theta. Okay, so that would be the definition of work. So now we go to kinetic energy. Kinetic energy. And what we do here is we consider a one-dimensional problem where we're applying the force and moving something along the, say, x-axis, going horizontal, say going this way. And let's assume here that there is no friction between the block and the floor. So we might say here we have like an ice cube, say, that can move very easily. Because see, now when I apply the force, I'm going to start accelerating because F equals ma. And that's going to convert, see that we're putting things here, the energy, the work that we're doing is going to go into motion. And that's going to bring us to an important conclusion. Now, if you have the force, which is constant, then F equals ma, the acceleration is constant. And if you're going to say, in this case, we could say we're starting at some velocity already. Say this thing's already moving at some velocity, v naught, and then the force is being applied. You start the clock, and then you're going to move a distance during that time frame, and that distance is what's important for us. And then what would be the velocity at the end of moving that distance, say from here, and you're going to go to some, say, place there, and we're going through a distance d. All right. Well, we've already done a problem like that. If you have constant acceleration, we have one of our four formulas, and one of them is that 2 times the acceleration times the distance traveled is v final squared minus v initial squared. It's a formula we derive in kinematics. So we have our answer. So therefore, for the work, we're going to look at this force times d translates into this change. And if I want to know what the actual work is, what I'm going to do is I need to take this A and stick it up in this, I need to put that A to this equation. So if I do that, I have M. So what is A? Well, it's going to be V squared minus V naught squared divided by 2D. All right. That's what the force is. But then when I find the work, I need to multiply the force times the distance. So I really want MAD. I want this. And that D is going to cancel. And I'm going to have 1/2 M V squared minus V naught squared. So really I want this. So I should have probably written this one down first, that the work is force times the distance, and I put the MA here, and then I substitute for the acceleration based on my kinematics. So in other words, the work done is 1/2 mv final squared minus 1/2 mv initial squared. That 0 there refers to the initial velocity. Now, this is special. Like, what is this? This is a energy that is greater than what we started with because we did work on the system. So we're going to define K. It's a capital K here. It's 1/2 mv squared is the definition of the kinetic energy. So when we look at a situation where we're looking at different forces, where force depends on your X, where you are. And to make this a little different, I'm going to say where you have some kind of ball and we're in outer space and we're moving to the right. Let's say we have Superman, which is a movie just came out, by the way. The new Superman movie here, I believe it was July 11, 2025. So Superman pushes this, but the force is a function of X. So at different positions, Superman may push more or less. So if that's the case, what we want to do for the work, we want to generalize this to an integral. So we have the force of X and a little delta X, a little differential X for that value. And we're going to go from X naught to X. Now, with Newton's law, what we're going to do is we're going to replace the force with a mass times acceleration. All right, but now the acceleration is not constant because that force is not constant. But now we're going to do a little trick here. What we're going to do is we're going to write for the acceleration the change in velocity with respect to time. And then we're going to do a little differential substitution and replace the dx with dx dt. All right. Now, if you're worried about the differentials, because you should never say this cancels this, you should never say that. But you could always make this friendly by saying that's a delta x over a delta t times a delta t. And now you could say the delta t is canceled. But when you take limits, you want to be very, very careful that you don't get cavalier and start canceling differentials around. But this would be equal to delta x. And in differential form, infinitesimal form, we write it like this. So now that we have that, let's go ahead and see what we have here. We have w is, and now we can go with a change of the variable. Since we have a dt instead of dx, we integrate with whatever the corresponding t is, which we're going to take that to be time is equal to 0 when we start going, and then we go up to t, and this is going to be m dv dt, and then dx dt dt. Now at this point, we're going to notice that the x dt is your velocity. So I'm going to write this as, and I'm going to also bring this m outside since it's a constant. And we're going to go here from 0 to t. And we're going to have v, I'll put the v first, and then dv, dt, and dt. And then with the similar trick, if you wanted to let these actually be deltas, so you could then, think of the cancellation and then proceed carefully with the limit, we can then, by transforming in that fashion, this becomes a dv, and we're integrating from the initial velocity that corresponds to time is equal to 0 to v, and it's going to be v dv. And now this is amazing. We're getting the same result as we had before. Because watch this, when you integrate this, you get v squared over 2. And when you go from v naught to v, so here we're going to get 1/2 m v squared minus 1/2 m v naught squared. And that's a very, very, very important equation. Now that brings us to C, the work energy theorem. And the work energy theorem states that the work done is equal to the change in the kinetic energy. And we're assuming here there is no friction, because if you push this across the floor like we did with our folks pushing appliances like this, then you start with velocity 0, you push it, and you have velocity 0 when it's over here. still at rest, or it becomes at rest again, and you move a certain distance d, and you applied a certain force F. So what happened? Well, what happened there is that you had friction between the appliance and the floor heated up. The energy went into some other forms. The other forms, you would hear noise and scraping, and you would have heating and maybe ruin the floor, something like that, scrape the floor. So here we're assuming in this case that there is no friction. So you apply the force, and then all the work goes into the change of kinetic energy. So that's the work energy theorem. And you might just note that when we talk about the force, in this case, we mean the resultant force, which is the net. It's a fancy way of saying you want the net force, because you could have more than one force acting on a body, and it would be the net force in the direction that you're moving. Now let's do a simple case where we have a ball, and we're going to drop it and let gravity work on it, and we'll assume no air resistance. So then the force due to gravity is mg, and g is the acceleration due to gravity, often given as 9.8 or 9.81. When you round off, it's 9.8 meters per second squared. And we're going to see later in our course that this varies from different places on the Earth. And here, if we look at the work done and say it falls a height h, right, and say we drop it from rest. So say it starts out at rest, so that means the initial velocity is 0, and then you just drop the ball, and then the ball falls down. And what is right before it hits the ground when it falls a distance h? So that would be then mg, that's your force, times h, and that has to equal the change in the kinetic energy. Well, if you start off with no kinetic energy, that means 1/2 mv naught squared is equal to 0, and that's when you start from rest. There's no velocity beginning. And then at the very end, right before it hits the floor, you would have 1/2 mv squared. Now notice that the m's cancel, that no matter what mass it is, it's going to fall at the same rate. So that means that if you drop a feather and, say, a ball at the same time, let them go at the same time, they're both going to get to the ground at the same time. Now, with a piece of paper, if you do that, there's a cushion of air and the paper doesn't fall down, but a very dramatic demonstration class is then to take the paper and crumple it up and then drop it with the shoe. I do this in class, and then they both go down at the same rate. There was a famous experiment done on the moon where astronauts dropped something that, like a feather or something light, and a golf ball or something, and they both fell at the same rate. So that means here that 2gh is equal to v squared, and look how fast we get the velocity. The velocity is the square root of 2gh. Now that's amazing, because when we do kinematics, we have formulas like the 2AD is v squared minus v naught squared, but you see that's built in here. See, if you had your 2AD, your 2AD equals v squared minus v naught squared. See, this is g, and this is here h, and the v squared is 2gh. The work energy theorem pops it right out without even having to think about 2AD is v squared minus v naught squared. That's a general result that we have incorporated in our equations. So that's it.